不要要求到放在那里。
说一下你的
要放在哪里？睡觉的时候。下学期继续，下一节别上。下学期600人继续。
So at the end of class last time, there were a couple of questions, and I'm not sure I can answer them with what we've seen so far, but I'll give it a shot. So let's first of all, let's see where we were. So I've got, I'm going to post these slides later. Okay, so I'm going to show you some stuff that you see. All right, so I talked about Slack form, and I see that there's a small problem here with the screen, so I have to adjust. But anyway, so so here's the original problem. We're always going to assume it's got a standard form, and here's Slack form. So what do you think about Slack form? And this is really kind of, it doesn't matter so much today, but it's going to matter on Monday. So, so here you're defining one new variable for each constraint. So this new variable is called a slack variable, is the difference between the right-hand side and the left-hand side of each constraint. That's slack. That's why it's called a slack variable. And we just we're going to make that difference. We're going to assume that difference is non-negative. So because you have a feasible solution. So all the variables in our linear program, the original variables, the new variables, are all non-negative. Okay, so that's the slack one. And I think here's an example. Here's the example we saw the other day. So here's the original problem. And here it is in Slack form. All right, so so what you can see is I've written this in the format that I'm going to like. So I've got the objective function, its value is z, and you can see a number here, which in fact corresponds to the initial value of the initial feasible solution that we're going to be dealing with. And these are just the coefficients of the objective function. And here you see the slack variables, and then I've just subtracted the left-hand side to get this. Okay, so here you have it, and all of this is non-negative. So I'm not going to write this last thing. I'm just going to assume that all these things are non-negative. All right, so this is our slack form. Now, the nice thing about slack form, one thing is that it makes it easier to do this process I made explain, to make this process very systematic so we can come up with a nice algorithm for it. And the other thing about the slack variables is that they'll have a role in proving that this algorithm is correct. Okay, so somehow it all comes together at the end. And it's kind of these slack variables correspond to a dual problem that is a minimization problem. Somehow this works out. All right, so that was where we were, and then I gave this kind of thing a name. Okay, so so this kind of thing can be referred to as a dictionary,
okay, a dictionary. And so, let's see, I think the next slide shows, maybe shows what a dictionary is. Go there. Again, we saw that the other day, so we have the objective function, which is C, and you have a certain thing here, which is going to be this number v prime is in fact going to be the value of the objective function, and we're dividing the variables into two classes: the class N, which stands for non-basic, and the class B that stands for basic. Okay, so the basic variables are going to correspond to these guys here, and the non-basic ones are inside these sums. Right, so what's going to happen is that this dictionary, from this dictionary, we're going to be able to read off the values of all the variables, original ones, the slack variables, as well as the value of the objective function. So the assumption, and we're going to maintain this invariant throughout the algorithm, is that all of these variables that are not basic, the n variables, are going to be 0, and therefore the xi's, or I and b, are just going to be equal to the bi primes. Okay, so these, I put primes here because these bi prime and aij prime are not in general the same as in the original problem. Although, of course, in this case, they happen to just be the negatives. So they just happen to be the same, right? But after several iterations, these things are going to change. So we just put the primes. Okay, so we have non-basic and basic variables, and it's very easy then to read out the values, and that's where we were. Okay, so so if you look at it abstractly, maybe some idea of linear algebra helps, maybe not, maybe just intuition. So you can see that, in fact, the dictionary is defined completely by your choice of A's and B's, and that B, that C, as well as what B and N are, capital B and capital N. So you could specify a dictionary like this. You have a tuple, which is the non-basic, basic variables, the matrix of AIJs, and then there's the B and C, and then the objective value is part of it. So you can just, that suffices to specify it. Okay, so each of these dictionaries, each of these, I guess, slack forms corresponds in fact to some basic feasible solution. In fact, corresponds to, turns out, a vertex of the feasible region. That's geometrically, but and we'll see a picture of that in a moment. And pivoting is the process of moving from one dictionary to another dictionary. So you start with some dictionary like that, N, A, B, A, B, C, B, and then you go to N prime, B prime, A prime, whatever. Okay, so you have this idea of moving. And one thing that I want to note right now is that it's possible. You can see here, so this is the original objective value. This is the objective value after pivoting. So V and V prime, so I will have that V prime is bigger than or equal to V. So you're maybe going to improve. But it's also possible that you can stay the same. Okay, so it's possible that maybe these two things are equal, and that gets you to some sort of interesting complications. But let's not worry about that. So here's the idea. Okay, so you look at your dictionary like this. Here's the dictionary, and these are zeros, and these are just a di prime. And what you do is you look at the coefficients of this objective function, and you look for a variable xe that has a positive coefficient. Okay, so that means that if you pick that variable and you increase its value, you are going to increase the value of the objective function. Okay, now, how much you can increase that objective value depends on these constraints, right? So you cannot make any of these xi's negative, so you are limited in your increase by these things. So what's going to happen is we're just going to increase this value of xe, let's call it, as much as possible. And that's going to, in the process, make one of these xi's in the base 0. And so what will happen then is that xe will have a value, which is not in general 0, and xi, this other variable, is going to go to 0, so it's going to leave the basis. And that's why we have the terminology indicated there. So the variable x sub e that enters the basis is called an entering variable, and the variable that drops down to 0 is called a leaving variable. Okay, so every time we do this kind of operation, we're going to shuffle the dictionary around, and here's the example from the other day. All right, so here's the original dictionary. Okay, now this original dictionary works. It works because it turns out that it is feasible for our linear program to have x1 and x2 equal to 0. I'll show you a picture of that in a moment, but you can see that that none of your constraints forbids you from doing that. And in fact, if you set x1, x2 equal to 0, you're at the corner of the positive quadrant at that 0, 0 point. And so that's a vertex of the feasible region. And that's it. Now we look at the coefficients, and we can see that, in fact, coefficients of x1 and x2 are both positive in the objective function. Okay, so this leads to the first question that was asked the other day. So first of all, let's look at dictionary 2. So I said, well, it looks like x2 would give me more of a return than x1 if I increment it, right? Because it's got a coefficient of 5. So I guess I would prefer it to maybe x1. So if I were greedy, I would go with x2, and in fact that's what we did. Okay, so I went from what I did is I incremented x2, which was 0, to something, and that was limited. In fact, I think it was limited to at most 3. So we pushed it all the way up to 3, and in the process, x5 became 0. Okay, so what happened was that x2 entered the basis and x5 left the basis. Right, so that was it. So the question that was asked was, what would have happened if I had chosen to increment x1 instead? Would that have been okay? Yeah. Okay, so it would have been okay to go that direction as well. Either way would have worked. There is nothing that says, at least as far as I know, that in general it's always better to go with a larger coefficient. It might not be. Why might it not be that great to go with the largest coefficient? You might have more of a, well, okay, so you go with it. It just doesn't depend only on the value of this coefficient. It also depends by how much you can increment it, that variable in it. You might be more limited for the one with the larger coefficient. So I don't know. But anyway, so we went with x2, and then we did this math. Now somebody corrected me, and actually everybody corrected me, and you were right. So here's the new dictionary, and then what we have is that only x1 has a positive coefficient. But you see now, in fact, that in this dictionary, the value went from 0 to 15. You can also see how the B's have changed, right? So we're 493, now they're 734, and the A's have also changed, and the basis has changed. So, but that's just reflected in the coefficient. So now I pick x1 as my entering variable, which is my only choice, and that is limited by the second constraint. And so what's going to happen is I'm going to push x1 as much as I can up, which I think is up to at most 1, and x4 will drop to 0. And here we go. This is the same thing, and we end up in this dictionary. All right, so in this dictionary, what we have is that the objective value is 22, so this is our b, little b, 22. And here are the coefficients of the objective function. So they are, now I have x4 and x5, they're minus 7/3 and minus 1/3. So that means that whether I increase x4 or x5, whichever I do, I'm going to only be decreasing the value of the objective function. So therefore, this must be optimal. Okay? Now, that's not really a proof, but if you look at a picture, I think that's the next. I think that is indeed the next thing. So here's the picture. Unfortunately, the colors aren't coming out right, but I'll have to live with that. Okay, so here's the initial dictionary, and here's the final dictionary. And I've numbered, I put letters next to the constraints, A, B, C. And, okay, our initial dictionary corresponds to x1, x2 equal to 0. So in fact, our starting point is this corner. Right now, as you see, the direction of optimization is given by, well, it's 2x1 plus 5x2, so it's actually going like this. So these lines here are just sort of the lines of constant objective value. So for instance, here you have an objective value of 10, then it's 15, and at this point it's 22 for all the points on this line. And in fact, of course, this would be the optimizer, the farthest point in that direction. So, so let's see, what happens is that we started here, and we, in fact, which way did we go? We went up this way, right? We went up this way and we ended up in this corner. So this was our second dictionary corresponded to this objective value of 15. Okay? And I'll let you look at that on your own. And our final dictionary, which is shown here, corresponds to this vertex. Okay, so we pivoted from here to here and from here to here. All right, so okay, so here's the coefficient. So you can see here that one thing is that this vertex is the intersection of the bounding line for constraint C and the bounding line for constraint B. Okay, so that's that vertex. And you can see that, in fact, in the objective function, in the final dictionary here, these are precisely the, or actually the slack variables that appear here are precisely the ones that correspond to those two constraints, x4 and x5. Okay, so they're the ones that define that vertex. Okay, so in fact, if you look at the previous step, you'd also see that the intermediate one between these two, you'd see that whatever appears in the objective function corresponds to this vertex, the previous one before you capture the objective function. So somehow these slack variables are, of course, telling you which constraints are tight, so they're telling you which vertex you're in. Right, so that's something. And in fact, then this leads me to the second question that somebody asked at the end of class. This is a fairly deep question, actually. Okay, so what do these things mean anyway, right? So, okay, so I don't know how many of you know or like linear algebra, but as this person noted the other day, it turns out that each of these dictionaries defines a basis for our two-dimensional space. So in fact, for instance, our initial two constraints where we start here, or what defines this initial vertex are these two constraints that go like this. Okay, so that, in fact, they're two orthogonal, in this case, vectors, and their linear combinations span everything. Okay? Now, what happened was that in this particular choice of bases, this vector that defines the direction of maximization is actually contained in that space, right? So you can actually, there's a way to move inside that space so that you increase the value of the objective function. And in fact, that's also true even when you go here, because you can still go, when you're at this vertex, what defines this vertex is the intersection of this line and this line, which is another pair of vectors which define another basis for space. And it turns out that, yes, you can go in that direction and still optimize. But when you get to this point, you've kind of reached the cap. So you can't optimize in that direction. Okay, once you get to here, I mean, you try to go this way and you're not going to be able to, because this is an extreme point. So there's some geometry here, there's some deeper sort of linear algebra thing that's happening. Part of what we're going to do on Monday is try to address that. All right, so that was my review. Okay, now there are a couple of things that we need to do now that I need to specify. All right, so the first thing is something called cycling. Okay, so here it is. so first of all, there is cycling, and I'll tell you what that is in a moment. And then there's the possibility for unboundedness. How do you test whether your linear program is bounded or not? And finally, there's a question of how do you get started? All right, so in this example, that the one we've been playing around with, it was very easy to get started. That is to find an initial basic feasible solution, because I knew that the origin was a feasible solution. Right, so that's easy. I can just start here, and then I can go from there. But in general, it's not so easy or not immediate to find the starting point. So we need to address that. All right. So so the first thing is cycling. So cycling is the possibility, which you'll never encounter in this kind of problem, this small one. It's the possibility that you do not get any improvement in the objective function. Okay, so it's possible that you go through a series of pivots, and in this series of pivots, which are all different dictionaries, you get exactly the same objective value. Okay, so that is possible. And the danger with that is that if you start doing that, you could go back to where you started. Okay, so you start with one, then you go back, and then finally you're back where you started. So that's going to be a cycle, and you're never going to break out of it. I don't know who discovered that possibility first, but it's been known for a long time that can happen. And if you go and you search around, you'll find several papers on that topic. All right, so I don't want to talk about all those papers because it's a lot of stuff and it's just more than I need to know. Okay, so there's a possibility you can have successive pivots with the same objective value. And one reason for this is that it is possible, maybe not in 2 dimensions, but higher, it's possible that the same vertex can be defined by various different sets of constraints. Okay, that if you just think about it, can you? If you think about it, okay. So it's possible. So I realize that either you seem to have a natural geometric intuition or not, but you can think about it, it's possible. So anyway, you can get stuck on a vertex, and if you go back to it. So people have looked at this, and there's different ways to attack this problem, and one way is called Blanch rule. So you always, if you're given a choice of entering, if you have multiple choices for entering or leaving variables, you always pick the one that has the smallest index. Okay, so always the one with the smallest index. Somehow magically, that guarantees that you'll never cycle. The proof of that, I'm not going to do it. It's not even, in fact, the proof is not even in the Corpman License or Westenstein book. I think I've read it once. It's sort of cute, but it's not really so important. Okay, for reference. Okay, so first of all, cycling, okay, it's a possibility, but you can avoid it using this rule by Blanch. Okay, so when I say, by the way, when I say index, I mean, if I'm talking about a choice between x2 and x5, the smaller index is the one that has index 2. Right, that's what I mean. Not values or anything, just the indices. And that just works. Okay, so that was the first thing. Yes, question, yes.
I just want to check my geometric understanding of cycling. It's like cycling is when you have like a set of vertices that are like on a hyperplane where the objective function is like all the same.
It's actually have a vertex that is defined by multiple constraints. Right, so you know if you have in 3 dimensions, it's actually imaginary. But you have 3 dimensions, you need 3 planes to define that vertex, but you might have 6 or 7 or 8, and they could all define that same thing. Yeah, and then of course the pivot thing would try all of them, and then you'd eventually go back to where you started. There's a nice example of this possibility in the Corpman License and Westenstein book, that chapter 29 that I mentioned. So if you go there, you'll see an example of that happening. So it remains there. Yes?
Just to be clear, in cycling, we don't actually change the geometric point that we're at.
You're there.
And there's just things like vertices with respect to like different planes?
It's
or
the same,
bounds?
it's the
Like-
same vertex, I mean, it's, I can't draw it, but, right, so if you had something like this, okay, so this vertex here in 3 dimensions, okay, so this is a vertex sticking out, can be defined by any 3 of these. So
Yeah, but you can draw another one that also goes through there.
sorry, you can draw another what?
You can draw another plane that goes to, those are the like standard planes. You can draw another plane that goes to the origin.
Well, this is not the origin, I mean, this is is in 3D, so I'm looking at it from
Right, just
above.
an example.
Sorry?
This is an example.
An example of?
Of-
All right, so it's hard, but if you look at it, you know, in 2D, I guess you could actually have multiple things too, right? I mean, you could conceivably, although I don't think in 2D it actually happens. So you have a vertex like this, and this, in fact, the feasible region is here, but then you have 2 others that kind of go through the same thing, right? So you could have that as well. But I don't think you can encounter cycling in 2D. In any case, we can avoid it. And I think even if you took no precautions for cycling, it's a very low probability event that it could happen to disaster. Okay. So other questions? All right. So we have okay. So Lions rule. Never mind. Okay. So that's sort of okay. The next thing is also not too bad. So the next thing I have to deal with is unboundedness. So remember what happens when you're in unboundedness is something like this. Maybe you're okay. So you went maybe like this from one starting basic feasible solution to another, and eventually you get to a point where you discover that you can optimize, you can go, you know, forever in this direction, and it's never going to, you're never going to be limited by how much you can increment your objective function. Okay, so that's the meaning of unbounded. So, what happens? Well, what happens is that we are still moving from vertex to vertex of the feasible region, but what will occur is that when you get to this point and you see that there's a coefficient, there's a variable with a positive coefficient that you can increment, you will discover that that variable is not limited. There's no constraint that you can put on it. So if you turn this corner and you find there's no limit on how much I can increment along this edge, then you know that your linear program is unbounded. All right, so the idea is, I just wrote it down, this is exactly what I just said. So it encounters a variable or an index such that the corresponding variable has a positive coefficient. There's no constraint that binds xe, and you can therefore make the objective function as large. All right, so let's just summarize it. So here's the summary. This is pretty much how simplex is described in Corbin, Leisten, and Rivest. So let's first of all, this is my notation for a dictionary. Okay, so dictionary is given, remember, by the non-basic, the basic variables, the A matrix, the B matrix, the C, the cost function, and the value of the objective function. Now, in here there is this method that I will define later. It's called initialize simplex that will construct the initial feasible solution. Now, of course, if the origin is feasible, then you would just use that. But in general, it may not be. All right. So then there's this loop. Okay. So this loop, you just find. So you find, well, first of all, you ask, is there some coefficient in the objective function that is positive? And so I just pick 1. This is going to be my entering variable. And then what we do inside this loop is we just determine the constraints. So this delta I would be the limit on how much I can increment this particular xe. Right? So if you look at the constraint, what you have is what you have is that, what is it? 0 bigger than or equal to bi minus ai xe, something like that, aie. So you have, if you look at just at that one, at each constraint in your linear program, it's when you just forget about the remaining variables, non-basic variables, and you just set this to 0, you have a constraint like this, and therefore this means that xe is less than or equal to bi over aie. Okay, so it's just looking at each of the constraints, and then you just do that. And of course, if it's bigger than 0, then it is a constraint. Otherwise, it's not, and you make that delta I equal to infinity. So delta I is the amount by which you would be able to increment this variable xe. And I picked the smallest of these delta i's because, of course, I don't want to make my solution infeasible. And but on the other hand, if delta L is infinity, that means that I can go forever. There's no constraint at all on how much I can increment this variable. So so that means that the problem is unbounded. So this corresponds to the case I just erased. And if not, then that means that you can pivot. Okay, so pivoting means going from one dictionary to another. And the pivot, of course, depends on the dictionary and also your choice of leaving and entering term. Okay, so this is just one pivot step. So you determine what the bound is. If there is no bound, then you declare the problem is unbounded. Otherwise, you pivot, get a new solution, and you keep doing this. So you keep doing this, and when you can't do it anymore, you stop. And when you stop, all you do is you just return the value of the variables associated with that final dictionary. So for each index in the basis, you make the corresponding xi equal to that b. Otherwise, it's going to be 0 because it's non-basic. Okay, so the first, the while loop here is just pivoting, and this just reports the answer. All right. So any questions? Okay. All right, so that summarizes it, but now I need to figure out how to get started. Because this is the sort of the final step that I need to cover. And okay, so I think this is unfortunately the red doesn't show, but you can see this is a 3V from Wikipedia. This is a simplex going down up a path to the optimums. Okay, so the question is, how do I find the starting point? So let's look at, in fact, how do I do this?
Quick question.
Yes, go ahead.
So earlier you said like if we knew that the origin was in the feasible region, then we would just use it.
Yeah.
But is that the case even if it's like strictly contained within the?
It's not negative. So it's always going to be a vertex in standard form. If it's not in standard form, it's not true.
Oh.
Okay. So yeah. So everything is modulo standard form. Yeah.
Can you find feasible point here and then move the whole thing to like the pointing 0, 0, 0?
Yeah, but actually you'd have to move the whole thing into the 0, 0, 0. You know?
Yeah, you know, back to
Yeah, you could, but then you'd have to transform the whole thing. I don't know. Maybe it could be possible. It might work. I don't know. But anyway, for everything I say here, there's probably another way to do it. But the nice thing about this is all standard, so it'll all work in any circumstance, under any kind of condition. Okay, so I want to find the starting point, and as I said, if it's 0, if my linear program has 0, 0, 0 as a feasible solution, then I'm fine. Otherwise, I'm not. And here's an example of where I'm not. And unfortunately, again, the colors don't work, so you can't see the red. But here's the thing. Okay, so this is pretty much, I think, the same problem as before. Same as before, except that now I put in a negative 1 here. Okay, so you can see here that I cannot just use x1, x2 equal to 0 because 0 is not less than negative 1. All right, so really, as long as these had all been non-negative, this and this is in standard form, my choice of x equal to 0 would have been feasible. But as long as you throw something, as soon as you throw something like this in, then it's no longer feasible to use the origin. Okay, so basically what happened when I added this constraint, if you think about it, is I just chopped off the origin, right? And then I can't use it anymore. All right, so I need to find a way to get to some point in the feasible region from wherever I am. All right, so let me maybe, I don't know if I can just skip some slides before I give you the theory. So here's what I'm going to do. It's a trick, and I know this is not the only way to solve this problem. Okay, I know this, but this is what several people use. So I'm just going to use it. So I'm going to introduce another variable. Okay, so I'm going to introduce another variable, and this variable is going to be x0. So let's just look at this. Skip this. Okay, here's my original problem. Okay, original problem, and okay, with this funny constraint here. And here's my new problem. Okay, so in this new problem, I have I've replaced the objective function by this by negative x0, where x0 is a new variable, and I have added negative x0 to all the constraints, except of course here, that's going to make x0 be non-negative. Okay, so I just subtract away those. Okay, so I now know that for sure this problem is feasible. Right, so I can set x1 equal to x2 equal to 0. And what choice of x0 would I have to make so that this is feasible? What choice of x0 if I choose x1 equals x2? Minus 1? It can't be minus, right? 1. Okay, so if I make x0 equal to 1, I have a feasible solution for this problem. Okay, so I know for sure that this problem is feasible, but it's actually not exactly what I need to solve to get a feasible solution for this problem. It's in that, I'm heading in that direction, but I'm not quite there. Okay, so I know this problem is feasible. Now notice that what I'm doing here is I'm maximizing the negative of x0, so I'm actually minimizing x0. So here's the claim. Let's write it here on the board. All right, so my job is to determine if my original problem is feasible or not. That's part one. Part two is, of course, if it's feasible, I would like to also have a basic feasible solution for it. Okay, so the claim is that the original problem is feasible if and only if the optimum objective value for the auxiliary problem is, okay, so the auxiliary problem being this problem where you're trying to maximize negative x0. So when is the original problem feasible? What does the objective value for this auxiliary problem have to be? Well, I want this set to be feasible, right? So I want there to be a solution for this. Now, of course, if I subtract enough, I'm going to get a solution, but I don't want to subtract anything. So what should this be? 0. Okay, so if all these are zeros, then of course the maximum is 0 because the value of this is 0. And that's obviously the largest you could possibly get because x0 is assumed to be non-negative. So the largest objective value you could get is 0. And that's actually the objective value you want because when you get 0, then you have a solution to this problem, original one. Okay, so if and only if the optimal objective value for this auxiliary problem is 0.
Okay, so now if I can solve this problem,
I have a solution. I know there's a feasible solution for this problem. Actually, if this problem has a 0 solution, there is a feasible solution for this problem.
all right, so I did this in this case, but it's true in general. Okay, so it's true in general. If I have any kind of problem where I'm not sure that where the origin is not a feasible solution, I can always test feasibility using this auxiliary problem. And I know this auxiliary problem is always feasible because of its definition.
Okay, so I reduced my feasibility to a linear program to feasibility of some other, or actually optimization of some other problem, which is the auxiliary problem. All right, so that's my idea.
Okay, so here's what I want. Okay, so the initialized simplex is going to take as input a linear program in select form given by A, B, and C,
And it's either going to return a dictionary corresponding to a basic feasible solution. Okay, it's either going to do that, or it's going to say it's infeasible. And I guess the or should go up there, not here. But okay.
So the method is going to be to set up this auxiliary problem and try to solve it. All right. So I'll tell you a few things about how you do this, but I'm going to glide over several details. If you want to see all those details, they're all mentioned in the Corbin-Lyson Rivest and Steinman. Okay, so here's the idea. Okay, just the idea. So here's the auxiliary problem in slag form. Okay, so I've just taken this problem and put it into slag form. Okay. Now, I want to solve this auxiliary problem using simplex, because that's all I have right now. Okay, so simplex is my method. So I want to use simplex. And I'm going to start at, I need to start with a basic feasible solution. So, so let's set up a initial dictionary, and you can see it here. I just added these auxiliary variables, or these slag variables, x3, x4, x5, x6. All right? Now, if I just do it like this, this is not a legal dictionary. And the reason it's not legal is because it has to correspond to a feasible solution, assuming the variables on the right-hand side are 0. If I set all these to 0, x6 is going to be negative. So this is not okay. Okay, so this is not a legal dictionary for the auxiliary problem. It's not. But there's a little trick, which is very simple, in fact, incredibly simple, which in one pivot allows you to go from this, which is not a valid dictionary, to a valid dictionary. So what you do is you just look at the most negative of these B's and do a pivot. So you just pivot x0, you make x0, enter the basis, and this variable, in this case x6, leave. And after you do the pivot, by the magic of simplex, you get a starting basic feasible solution. So it's a pivot. Now, one kind of weird thing about this pivot, what can you tell me about the objective function when I went from here to here? It decreased. Okay, so this is a funky pivot because it actually decreases the value of the objective function, but it gets you into a basic feasible solution. Okay, so now once you have this basic feasible solution for the auxiliary problem, you just start pivoting, 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 and if your optimum solution is 0, then you know that the original problem is feasible, and if it's not, you declare it to be infeasible. Okay, so you just use simplex to test that. So the lemma, which I'm not, so it's a general form, but the fact here is that the original linear program is feasible if and only if the optimum objective function for the auxiliary problem is 0. All right, questions? So here's here's a summary. Okay, this is a summary of what we did today. All right, so given any linear program, simplex will, first of all, either report it's infeasible or it's unbounded, or it will terminate with a feasible solution in at most this many iterations. Okay, so n is the number of variables, m is the number of constraints. Okay, n is the number of x's initially, and m is the number of constraints. Okay. So the case of infeasibility is guaranteed by the initialize simplex method. The initialize simplex method will check if the problem is feasible by setting up the auxiliary problem and seeing if that has an optimum value of 0. Checking for unboundedness is done by that's line 11, where you check if, well, if there's no constraint that binds your entering variable, then of course your linear program is going to go forever. Okay, you're going to be able to increase the objective value by any amount you want. Finally, as far as termination, this is actually kind of interesting. So if we use Bland's rule, first of all, we know we're never going to cycle, so we're always going to encounter different dictionaries. And it can be proved. It sort of makes sense intuitively, but you just have to do the algebra. You can prove that each dictionary is uniquely determined by your choice of basis. So once you've chosen a basis, everything else follows. So your basis is determined by a choice of m variables that are in the basis. Okay, initially those would, each of them corresponds to a constraint. So you have m variables which correspond to the basis. And so you have n plus m variables that you can choose from, including the original ones and the slack variables. And the basis has size m, so you have m plus m, choose m possible dictionaries, and that's how many iterations there are going to be. So what I haven't proved here is that what you get is optimum. Okay, there's no proof here. Okay, so let's see, I have one final thing I want to do today. Okay, so let's see. Okay, so here. All right, so let's go back to this. This is my final dictionary, has minus 7/3 multiplying x4 and minus 1/3 multiplying x5. And x4 corresponds to constraint B, and x5 corresponds to constraint C. All right, and in fact, if you think about it, let's see, so A3, yeah, so, and here, of course, x3, the slack variable corresponding to the first constraint is multiplied by 0, right? Because there's no x3 term here. Okay, so what happens? Well, let's do the following. Then let's take the negatives of these values. Okay, so I'm going to do the following. So so I have x3 is multiplied by 0, x4 is multiplied by negative 7/3. I'm going to put 7/3 here, the negative of that. And x5, which corresponds to the third constraint, is multiplied by 1/3. Okay, those are the multiplies that appear in the objective function. Okay, so if I take 0, let's see. Oh, this is going to be kind of cool. Go back. Okay, so go back here. Okay, so go back here. So I'll let you test this. But if you take 0 times this, the whole constraint, plus 7/3 times this, plus 1/3 times this. You take these constraints, add them up. Okay, what you get is that 2x plus 1 plus 5x2 is less than or equal to 22. Okay, so you end up, so you get, in fact, that, again, you multiply each of those constraints by the corresponding number here, and you'll get that 2x1 plus 5x2 is less than or equal to 22. Which means that the objective function was never going to be, ever going to be larger than 22. And that means that because we got 22 as the optimum, as the final objective value, that 22 better be optimum. Okay? Now how did that happen is what we're going to see next time. I'm going to stop here.